Hi everybody, welcome back. This is part 2 of our VSEPR series on valence shell electron pair repulsion. And just as a reminder, valence, VSEPR. And how we're going to use this theory that electron groups want to be as far away, they repel each other, they want to be as far away as possible, and that is going to influence the electron geometry. There are 5 basic shapes that we're going to talk about in this video, and it's based on the number of electron groups. So we're going to have 5 basic shapes. So these basic shapes are based on the number of electron groups, and we need to define electron groups. So electron groups. And we're going to be able to determine these electron groups based off of the Lewis structures that we've been practicing. And I'll abbreviate electron group EG. Sometimes you will also hear electron groups referred to as what we call steric number, and that really is the same thing. And when we look at electron groups, we're looking for groups around the central atom. And this is going to allow us to expand this out to larger structures than just single central atom structures, because we're going to look at each central atom separately. So how do we define an electron group? So we have 2 types of electron groups. We have bonding groups, so which can be either a single bond, a double bond, or a triple bond. And then we have lone pairs. And each one of these can be a single electron group, whether you can have a bonding group or a lone pair. And then the total number of electron groups is going to be defined as the bonding group plus the lone pairs on the central atom will equal the electron groups. And then this again is referring to everything on the central atom. So let's do a few examples of that. Right here. So let's do a couple of examples. So if I look at a Lewis structure of methane, CH4, and in order to do these types of problems, you have to be comfortable with Lewis structures. Because if you don't start with the right Lewis structure, you run into trouble. So we're going to have the bonding groups, the lone pairs, and then we're going to come up with the electron group. So we have, let me pick a different pen color here. So we're looking only at the central atom. So the number of bonding groups around this carbon here, we have 1, 2, 3, 4. And so there are 4 bonding groups and 0 lone pairs. Right? There's no lone pair sitting on that carbon. And so my total is the bonding groups plus the lone pair. So my total here is 4. Let's make room for some more examples. The next example that I want to look at is carbon dioxide. We looked at that in the first video when we talked about carbon dioxide. And we can draw a carbon dioxide Lewis structure here. It's double bonded to 2 oxygens. So. And we got to first identify bonding groups. So the bonding groups here is 2. Be very careful. Do not calculate each line separately. A bonding group, this is the double bond indicates there are 4 total electrons or 2 pairs of electrons, and that is 1 bonding group. A way to keep this straight and keep your mind from calculating saying the bonding groups here is 4 is to say, instead of bonding groups, think about this as atoms attached to the central atom. That way you will never double count, okay? So for carbon dioxide, there are 2 atoms attached to that carbon, so I have 2 bonding groups. The lone pairs is still 0 here, and so the total number of electron groups here is 2. The last example I want to look at is SF4, where we have sulfur, here, and then I'm going to draw these in my external lone pairs. All right, so again, let's look at the bonding groups. Here I have 1, 2, 3, 4 bonding groups. And in this case, I have 1 lone pair. For the lone pairs, only the central atom. Don't be tempted to count all these lone pairs sitting out here on fluorine. All that matters when we're coming up with geometry is the particular central atom that we're looking at. So I have 1 lone pair, and so my total here is a total of 5 electron groups on the central atom. So we can do this with any Lewis structure that we have, etc., etc. So it's good to practice that, identifying your bonding groups versus lone pairs. Now we're going to use our knowledge about our bonding groups in order to figure out and look at the 5 basic shapes for electronic geometry. So we're going to talk about electronic geometry. In the next video, we'll talk about derivative shapes, but right now we're just going to look at the 5 basic shapes that I alluded to. So the 5 shapes. And electronic geometry doesn't distinguish whether I'm dealing with a bond or a lone pair, just the total number of electron groups. So electron groups So if I have two electron groups, I have the general structure of A X2, and a little bit that this A here can be any central atom, and that bond can be any bonding group. So it can be either a single, a double, or a triple bond. It doesn't matter. I'm just kind of showing the attachment there between the atom. And then X can be an atom or a lone pair. Okay? So don't worry too much about that. Just kind of A has two different electron groups around it, whether a bonding group or a lone pair. And the idea of valence shell electron pair repulsion. So let's kind of jot that out again. VSEPR, valence shell electron pair repulsion says that these electron groups, whether it's a bonding electron group or a lone pair, wants to be as far away from each other as possible. And so if I have two things as far away from each other as possible, what's the farthest they can get apart in three-dimensional space? And that is 180 degrees, which gives me a linear electronic geometry. So now let's take this out and look at three things as far away from each other as possible. So let me draw that a little more clearly here. So if we're thinking about three things as far away from each other as they possibly can be, they end up at the corners of an equilateral triangle. So these three things are moving around the central atom. They're tied. They're associated with that central atom, but it's as far away from each other as they can possibly get. It's going to be 120 degrees, which is the corners. So these X, whether bond or lone pair, is going to be at the corners of an equilateral triangle. And this gets the name of trigonal planar. And then we're like, I'll draw kind of freehand here, an equilateral triangle. And you can look at it like, here's my central atom. Here's my bonding or lone pair. And they're coming out to the corners of that equilateral triangle. And that gives me that angle of 120 degrees, and that's where it gets its name, trigonal planar. So let's continue this on. 4. So I have 4 things attached. Now, 4 things attached as far away from each other as possible. You might think it would go off to the corners of a square, but you really have to think about in 3D. And in 3D, we end up having this geometry called a tetrahedron because it can take up all of 3-dimensional space. And it will spread out a little further based on that. So instead of a 90-degree angle, which is what you would get on the corners of a square, you can get 109-degree angles. And I'm going to draw this with wedges and dashes. And this wedge that I'm drawing means it's coming out of my board here to try to give it some 3D. And then going back here, I'm going to use dashes, and that's coming back of the board. And the best way I can draw this is kind of like a little tripod. Sometimes I call it like a little spaceship. It's called a tetrahedron. And I'll try to draw it better here. So it's like a square pyramid. And you have your central atom in the middle of that pyramid. And then my bonding groups are coming to the corners here. So here's my one coming out. That's going back to that back corner. This one's coming out, and then that's coming up there. So it's the corners of that square base pyramid. And this gives me angle of 109 degrees. We have two more shapes I want to look at. And this is going to be 5 electron groups. And this forms what this does is it does like a triangle around the central. So that's the kind of that equilateral triangle. Hold on, let me try to go that a little less out of my way here. And then coming up and down in the plane, I have kind of these 2 sticks. So imagine this is like a triangle going around the middle of these 2 bonds coming out. And so in the middle here, this is to the plane. There's a 90-degree angle. And then coming around is a 120-degree angle. The ones coming up and down, try to get the color. The ones coming up and down are called axial, and the ones going around the middle are called equatorial. And this is called trigonal, bipyramidal, because it is a triangular based pyramid on top of each other. So again, I'm going to try to sketch this out here. So we have a pyramid with a triangular base. Yeah, sorry. Let me try again. I'm not the best drawer here. kind of this diamond. And then a point coming out. And so we have the up and the down, and then coming out at the corners, the three coming out at the corners of the pyramid. The last geometry that we have, it's very similar to the trigonal bipyramidal, but instead of 3 coming around the middle, I'm going to have 4 coming around the middle in terms of a square. So here I have A, and then I have my square, these are coming out of the board, these are going back in. And then this is coming again up and down. And so this shape is called an octahedron. And it's a square pyramid, like we drew with the tetrahedron before almost. Sitting on top of another bottom pyramid. And here in the middle I have the 4 coming out, and then one going up and one going down. Kind of like so. Maybe I should try to show that in some color. I think of this one kind of looking like a jacks, if you can visualize that. So I like to think about that like here, and then you have like the jacks, as opposed to the trigonal bipyramidal, which similar. It's got the one coming up and coming down, but we only have 3 little pieces coming out of it. Like so. So that's the difference between the trigonal bipyramidal and the octahedron. And so those are our 5 basic geometries. You can go back and review. We have linear, 2 things as far away from each other as possible. Trigonal planar, 3 things as far away from each other as possible. Tetrahedron, 4 things as far away from each other as possible. Trigonal bipyramidal. And so this is actually interesting geometry, that this is how we get 5 things as far away from each other as possible. And this is the only one that has 2 different types of angles in it, 120 and 90 degrees. 90 degrees right back from here to the equator. So from the axial to the equator, if you can kind of visualize it that way. And then 120 degree angles around. And then I realized we didn't do the angle here on octahedron, but the angle for octahedron is 90, again to kind of that equatorial portion, but it's also, because it's the center of a square, is 90 all the way around. All right, so practice these. Practice finding your electron groups and identifying the basic electronic geometry around a central atom. The next video we'll talk about the difference and how we characterize whether it's a bonding group or a lone pair group and how that affects our shapes. Thank you.